Topic of this video is vertical circular motion from SYJC lesson 1 rotational dynamics presented by Anita Jogrekar. Vertical circular motion. Two types of vertical circular motion are commonly observed in practice. One, a controlled vertical circular motion. In this case, the speed is either kept constant or not controlled by gravity. Example, giant wheel or similar games. Second, vertical circular motion, which is completely controlled only by gravity. During the motion, there is interconversion of kinetic energy and gravitational potential energy. Motion is non-uniform circular motion. That is, speed is not constant. Now let us consider a point mass, which we commonly call as bob, tied to a massless, inextensible and flexible string, which is whirled in a vertical circle, so that the bob, that is point mass, performs vertical circular motion and string rotates in a vertical plane. Now this is a simple diagrammatic representation of vertical circular motion. At any position of the point mass, there are two forces acting on it. First, its weight mg, which is always acting vertically downward and which is of course constant. Second force, the force due to tension in the string, always directed along the string and towards the center. Its magnitude changes with time and location. Now just have a look at the diagram. At topmost position A, you can see tension and weight are acting along same direction, whereas sideways position D, tension and weight are perpendicular to each other, whereas at lowermost position tension and weight are exactly opposite. Now we will try to find out, or we will try to formulate tension at different positions for a particle performing vertical circular motion. Tension in the string at different positions. This is a diagram for any random position. If r is radius of circular path, v is velocity at random position, t is tension in the string. Look at the diagram. Weight acting vertically downward, mg, tension along radius towards center. If we resolve the vector weight into its components, mg cos theta and mg sin theta. Now look at the diagram. Tension T and mg cos theta are exactly opposite, right? Then centripetal force, which is essential for circular motion, is net effect of these two forces, tension T in the string and cos theta component of weight, mg cos theta. So centripetal force mv square upon r is equal to T minus mg cos theta. This is for any random position, or we can write tension T is equal to mv square upon r plus mg cos theta. Now if we talk about specific positions, at uppermost position where theta, that is angle, is equal to 180 degree, cos of 180 is equal to minus 1. So at topmost position we get, if we substitute for cos 180, mv square upon r is equal to T plus mg, or tension in the string T is equal to mv square upon r minus mg. Whereas at lowermost position where theta is equal to 0, mv square upon r is equal to T minus mg cos 0. Cos 0 is 1. So it is mv square upon r equal to T minus mg, or tension in the string T is equal to mv square upon r plus mg. Right? This is about tension at different position. Now with this we will try to find out velocity at different position. Since it is a non-uniform circular motion, velocity goes on. Velocity at different position, same diagram. At uppermost position A, both weight mg and force due to tension. For position A, let us call tension TA, are towards center. If VA is speed at uppermost position, we get mVA square upon r is equal to TA plus mg. For minimum possible speed at this position, what is required? This tension, it just can be equal to 0. Alright. Then substituting this value, we get mVA square upon r is equal to mg, or VA, that is velocity at topmost position, is equal to root of rg. Now if velocity at this position is less than root of rg, what will happen? The string, yes, will it be in a position to complete vertical circular motion? No. It will come back to B from uppermost or topmost position. Right? So this is the minimum velocity required at this position to maintain vertical circular motion. At lowermost position B, force due to tension is vertically upward, weight mg acting vertically downward. If VB is speed at this point, then mVB square upon r is equal to TB minus mg. Now while coming from uppermost position A to B, vertical displacement is 2 times the radius. Decrease in gravitational potential energy is converted into kinetic energy. Potential energy, general formula is mg into h. If we assume B as lowest point 0, then h is equal to 2 times the radius 2r, right, for topmost position A. So mg into 2R is equal to, so this is change in potential energy is equal to change in kinetic energy at two positions. So mg into 2R is equal to 1 by 2 mvb square minus 1 by 2 mva square. 4 times gr, m gets cancelled. So 4gr is equal to vb square minus va square. But we know that velocity at topmost position A is equal to root rg. Therefore, 4gr is equal to vb square minus rg or gr. Therefore, we get vb, that is velocity at lowermost position, is root 5 rg. Position D, when string is horizontal, force due to tension and weight are perpendicular to each other. Tension provides the centripetal force and weight changes speed. While coming from A to B, vertical displacement is R. Previously it was 2 times R, right? When it is coming from A to B, vertical displacement is 2R. When it is coming from A to D, it is just R, equal to radius of this circular path. Decrease in gravitational potential energy gets converted into kinetic energy. Potential energy mgr is equal to 1 by 2 mvb square minus 1 by 2 mva square. Substituting for va, we get 2 times gr is equal to vd square minus rg or gr. Therefore, velocity at d is equal to root of 3rg. This is about velocity at different positions. In short, for particle performing vertical circular motion under gravity, tension in the string is maximum at the lowest position, whereas it is minimum at uppermost position. Speed is maximum at lowest position, whereas it is minimum at uppermost position. Thank you. If you have any difficulty, you can contact me in physics lab. Thank you very much.